Great, so thank you and good afternoon. Thank you for inviting me to share our experience designing and implementing interventions to increase learner engagement. So my name is Ponce, Executive Director of the MIT MicroMaster in Supply Chain Management. And let me start with the two principles we have with this program. So the first principle is to democratize knowledge. So we really want to provide education in supply chain management to anyone from anywhere, just with internet connectivity. The second principle is to allow them to earn a certificate at a modest fee, at a very reasonable price. So we are trying to pursue for these two principles in our program. We started in 2014, and to date we have run 29 MOOCs as part of the MicroMaster in Supply Chain Management. This is a global program. We have learners from more than 190 countries represented in this program, and more than 250,000 of learners have registered in at least one of our MOOCs. In terms of the program includes 5 MOOCs, 5 massive open online courses, all about supply chain management. Once they complete the 5 courses, they are eligible to take a final, comprehensive, and proctored exam. Why are we doing that? We really care in this program about assessment, and we really care about providing a rigorous assessment. And the reason is that we are providing, or we are granted, a MicroMaster credential. The MicroMaster credential is by itself a standalone certificate recognized by the industry, but it is also a pathway for credits to a master degree here at MIT. So those learners who complete the MicroMaster and apply for the master blended degree at MIT in supply chain management, we are recognizing to them 1 full semester of credits. They just need to spend 1 more full semester on campus, and after that, they graduate. They graduate as a Master of Engineering in Supply Chain Management. To date, we have granted 1,500 MicroMaster credentials, and 40 learners already graduate from the blended master degree. This happened last May 2018, and now we are almost about to graduate 36 graduates this June 2019. So these are the numbers. Why are we doing research, in particular this research in online education? Our main motivation is to provide the best learning experience through innovation and continuous improvement. We are continuously reviewing what we are doing. We are looking at our data, trying to learn from this experience, and based on that, trying to improve our courses. Our goal is to help learners to complete and succeed in a MOOC and also in the MicroMaster program. This a combination of 5 MOOCs plus the final exam. In this research project, in particular, what we are looking at is at the dropout problem. So let me share with you some data about the dropout problem. We have a look into our 2018 courses. We ran in 2018 10 MOOCs. We have more than 9,000 learners who are verified. We have 2 types of learners. Audit learners, they just enroll in the course, they have access to all content, but they do not have access to the credential. And we have those learners who pay for a fee, $200 per course in our case, and they at least show the intention to pursue for the certificate. So these are 9,700 learners. We also look into their performance, what they did, and we discovered that 32% of those learners who already pay for the certificate, they are dropping out. They are giving up the course at some point. So what we did is look a little bit more into our data, and we categorize our students in different categories. We call learners, these are those learners or those students who watch videos, and they also submit homeworks, graded assignment, midterm, and final exam. They are, let's say, active learners. We also have an 85% of our verified students, they are learners. We also look at those that just watch videos, but they don't submit any graded assignment. these are the 10% of our verified learners. We also have what we call zombies. These are people that they don't watch videos, they don't submit homeworks. Fortunately, they are paying, so they are kind of our donors, at least, but they represent the 5% of our verified learners. And we were really surprised because they at least show the intention to pursue for the certificate at some point because they make the action to buy the certificate. However, and then we have also magicians. Fortunately, we almost have 0% of magicians. These are people, they don't watch videos, but they submit homeworks. My boss called them magicians. I have a better name, but it's okay. So in any case, we look at these learners, and what we found is that around 30% of them, they are dropping out at some point. So how to solve this problem, or what is our approach to this problem? The very first thing we are doing is looking into the data. We are looking into the data. We are trying to better understand our learners' behavior. We are just investigating what they are doing through the platform, through the data that we have. Then what we are doing is applying machine learning techniques. We are developing predictive models in order to predict those learners at risk of dropping out. And this is the second thing we are doing. Based on this information, we are classifying our learners at those that are at risk of dropping out, and we are designing and implementing interventions in order to reduce this dropout rate. We are also quantifying the impact of these interventions, and what we are trying to do is learn from these interventions, from these results, from this quantification of the result, and see if the intervention is working, if it is not working. We are also taking feedback from our learners, from the surveys, from the email account that we have, and we are trying to incorporate this feedback in order to continuously improve the program, learn from our mistakes, learn from our learners, and trying to improve our courses run by run. So this is our approach. Today, I'm going to focus in the interventions. In those interventions, we have design and we have implementing. So I just pick 4 interventions. These are the most recent interventions we have implemented in our program. The first one is a course intervention. The problem here, we identify that in one of our courses, our learners were really struggling in one lesson. We identified that based on the grades, the average grade performance for this lesson was below the average grade in that course. And also, learners reported to us that they were spending more hours studying this lesson that we were expected. On average, we have designed the course to spend 8 to 10 hours per week of effort per student, and that week, that lesson, students were reporting 16, 20, 25 hours in that lesson. So what we did is we just refilmed the lesson. We refilmed the content. Dr. Chris Kaplis, the main instructor, redo the lesson completely. We also highlight the key concept of the lesson and try to make it or design in a more straightforward manner. We also add some recitations. Also redesign the graded assignment for that week. We quantify the effect of this action. We compare the results for this run of the course with the 2 previous courses. And we found that the dropout rate after implementing that was reduced, was 1.5% versus 5.5% before implementing this intervention. The second intervention we did is also a course intervention. In that case, the problem here is that we identified that the highest dropout rate happened in our courses right after the midterm exam. So we also look into the data, and we learned that in those courses that the midterm was especially challenging, the dropout rate was especially high. So what we did is we really want to keep the same level of difficulty in all of our courses and in all of our runs. What we did is just to try to, the most challenging question, move to the final exam instead of providing that during the midterm exam. And with that, what we observe is that the average grade performance in the midterm was a bit higher in the final exam was a bit lower than before. And finally, the effect on the dropout was we reduced the dropout in 4%. Before implementing that, the dropout right after the midterm was 8%, and after this redesign was 4%. Then we look into students. We decided to implement an intervention, was a student-oriented intervention. This was just an email, just to encourage our learners to take the midterm. Again, we have the issue that after the midterm, most of our learners give up the course, so we just send a note to them, trying to encourage them to take the midterm exam. We did an A/B test, and we analyzed the results. No impact here, no impact. Then we think about, okay, maybe it's because we just encouraged them to do something, but we didn't include any call for action. So we decide, okay, let's try to prepare some materials to do something to help them to prepare for the midterm. And what we did here is we prepared a recitation, was a prep material before taking the midterm exam. We also designed a list of key topics that they need to review before taking the midterm exam. And again, we conduct an A/B test, and we send these two interventions to the two groups of learners. No impact here too. So our takeaways. Still, we have the current challenge of trying to reduce the dropout rate, not only in a MOOC, also in a program. Because what happens is sometimes we're able to convince the learners to complete our MOOC, but we have 5 MOOCs and a final exam at the end in order to complete the MicroMaster program. So we are working in both sides, convince them to complete the course by itself and convince them to take the next and the next and the next one. Also, we still have room to better engage learners in MOOCs and in a MicroMaster program. The lessons learned from the interventions we have conducted so far. In our case, and based on our experiments, course redesign works better than student emails. In our case, we found that the student emails has no impact. However, those efforts that we did directly to redesign the lesson by itself had a positive effect. Also, the intervention I mentioned about to increase gradually the difficulty across the course. Regarding the next steps, one thing that we are also thinking about is we want to investigate if the channel is the problem here, because the email didn't work. So we don't know exactly if the student intervention didn't work because of the email by itself is not working in this case. So our next intervention that we are planning to implement is more focused on implementing that through the platform. So what we really want to do is try to tackle student factors, but through the platform. This is one thing. Second thing is we want also to better understand the reasons behind. What are the reasons for our learners to drop out? Based on the preliminary analysis that we have, in most of the cases are external factors, more than internal factors. However, this is something that we really want to continue exploring and investigating, and we have the plan. The immediate plan is to run surveys in order to better understand the reasons about why they are dropping out. And we are doing that because we want to tailor or customize interventions depending on learners' motivation. And also, another thing we want to do is, depending on how the learner is engaged with the platform, with the content, try to tailor these different interventions. We also know that some of our learners are taking the MicroMaster program because they really want to pursue to apply for a blended master degree at MIT. Some of them are taking the program because they just want to have the standalone certificate to apply for a better job. And some of them just want to learn. They don't want to have the certificate. So we really want to understand the motivation behind and try to tailor these interventions based on this motivation. Final lesson learned, to provide a massive online program with a high-touch experience and trying to engage learners with our program definitely takes a village. So I really want to acknowledge my team for the effort and the commitment with the program and trying to better engage our learners. So thank you.
Thank you. you can think about this as an attempt to try to see the connections between two fields, both of which are deeply tied to learning. So there is, of course, education, which is all about learning, and then there's neuroscience, also all about learning. But the phenomena that are explored in these two domains often are sufficiently different that we don't really see ways to connect one with the other. And we're trying to see if there might be at least some tenuous connections that can be discerned. So my lab focuses on the problem of plasticity. And we specifically work with children like this young boy who have been born blind. So born with cataracts that you see in the child's eyes, a condition that at least I used to think of as being associated only with advanced age. It turns out that children can also be born with cataracts, often because of maternal infections. But what we're doing is identifying these children and providing them treatment. So say at the age of 10 or 15 years, they begin to see for the first time. So it's a remarkable change, and we're trying to see how much vision can they acquire at that time. And the reason this is an interesting question to ask from the perspective of neuroscience is because of our conceptions of plasticity. So as this schematic shows, it's generally assumed that plasticity in the sensory pathways, like vision, peaks very early on in the first few months and then declines. And by the time the child is about 5 or 6 years of age, there's very little residual plasticity. So if that's the case, then such a child, if he is being treated at 10 years of age, is essentially out of luck. We might have corrected his eyes, but the brain simply doesn't have enough plasticity to make use of this visual information that it's now beginning to receive. But to our surprise, what we're finding is that even into the second decade of life, what you're seeing here are the neuroimaging maps for a 20-year-old subject. And without going into the details of exactly what we're mapping here, just at the top level, what you can see is within a matter of 4 months, so you're seeing the functional state of the brain at 2 days prior to surgery, a week, a month, and 4 months after surgery. Within 4 months of surgery, the brain is dramatically rewiring, suggesting that there is significant plasticity there. And if this video plays, it'll give you a very visual sense of just how quickly the child is able to make use. Yep. So what you're going to see here is about a 1-minute clip of a young girl by the name of Sumitra. She's 11 years old. First, you're seeing her pre-surgically, so she's blind here. But we have asked her to try to find a box of candy that we've put by the side of the hospital corridor. And it seems like a cruel thing to do, but we are documenting just how impaired her vision is at this point. She can essentially tell night from day, but no more. That's her father in the background. And next, you see her 8 days following surgery. So it's quite remarkable how much change can happen. And we also have lots of data showing that the quality of life of these children undergoes a dramatic improvement from pre to post surgery. So clearly plasticity is manifesting. And the question is, how are we seeing this plasticity? What is the source of this plasticity? If the initial resource of plasticity that we are born with, if that's declined to very low levels, how might we be seeing plasticity in these children? So in thinking about that question, one possibility that we are entertaining, and it may well be a crazy possibility, but the possibility is plasticity on demand. That is, instead of thinking of plasticity as a resource that simply decays with time, perhaps the brain can bring up added plasticity when the circumstances demand that it do so. So if you are immersed in a novel environment where you have a heavy load of learning the regularities, the statistics of the environment, then perhaps additional plasticity can be made available. And that's why we call it plasticity on demand. So this idea, even though it sounds kind of crazy, actually has a little bit of experimental evidence that's beginning to accumulate around it. Here's one paper that talks about this. So the immersion of an animal, or in this case humans, in novel environments seems to enhance plasticity in the parts of the brain that are concerned with learning and memory. So if there is anything to this idea, that exposure to novelty can enhance plasticity in some of the crucial parts of the brain, then applying this idea to the domain of education might suggest that if we were to take conventional educational material and we were to insert some novel interstitials in that material, might that transiently at least enhance plasticity and thereby increase the uptake of information in that material. And that's why the name of this project is Enhanced Learning Through Novelty Insertion. And these two arrows are supposed to be, with the insertion of novelty, you get an enhancement of engagement. And that, along with novelty itself, perhaps are leading to an enhancement of plasticity. So our hypothesis, the experimental hypothesis we have, is that the insertion of novelty in conventional teaching material would lead to an enhancement of learning because of an underlying enhancement of plasticity. As you might imagine, it would have far-reaching consequences if we were to find any evidence to this effect. So with this, let me invite Matt to tell you about some of the experiments that he has been doing.
So in order to test the effect of novelty on learning, we inserted a variety of videos into a downloaded lecture from OpenCourseWare. The lecture was Introduction to Psychology by Professor John Gabrielli, and we inserted two different types of videos. What we're calling familiar video, which was an instructional video on how to clean your kitchen, and the novel video being a series of an entertaining series of YouTube videos about nature, essentially. And before and after we had subjects watch this lecture, we had them take a pre-assessment with 8 multiple choice questions and a post-assessment after with another 8 multiple choice questions. And each of the post-assessment questions, I'm sorry that some of the slide is getting a little bit cut off, but each of the post-assessment questions was associated with one section in the lecture. So we can assess how they learned in response to different kinds of stimuli. And then in addition to that, we took some biosignals, ECG or electrocardiogram, like the machine you see in a hospital, and EDA, electrodermal activity, which is a measure of skin conductance. So the basic results first. So there was learning if you look at the pre-assessment and post-assessment scores, but in addition, there may also be an effect of novelty. They had, subjects in general had a higher score in the sections of the lecture that were following novel stimuli relative to the sections of the lecture that were following familiar stimuli. And this did control for the difficulty of the question in the sense that we had one group of subjects that saw the novel stimuli first and another that saw it second. So essentially, we run into one potential issue here, which is that we already know that arousal enhances learning. And what if the video itself is is causing an arousal response. So I imagined a few possible scenarios, and essentially what the plot would be is on the y-axis, performance in the questions on the assessment, and then on the x-axis would be the arousal during the section of lecture that had the content related to that question. So, and as a convention also, so blue is supposed to be novel and red familiar. So if you were to imagine that they had entirely different arousal responses due to the different types of video and a different performance on the post-assessment, we couldn't make a strong conclusion about novelty itself. But if we got a range of responses in arousal and then saw an independent effect of novelty, then we might be able to make a stronger conclusion that there was some other property of the videos other than just the arousing effect that caused the increased performance and learning. So how did we measure arousal? So we have two different types of biosignals, electrocardiogram, which we can infer from their heart rate and their heart rate variability, their level of sympathovagal balance, and from their skin conductance, we can talk about sympathetic activity, sympathetic nervous system. So this is the pipeline, essentially. The main output of our pipeline is a set of time series, which are basically indices of arousal, and we have a set of different features. So we can compare those features. This is an example of looking at the EDA peak rate slope for different sections of the experiment and ask some basic questions. So is there a difference between their arousal during the novel videos, the familiar videos, and the lecture? Definitely. We saw a significant difference there. And is there a difference due to like the first half of the lecture versus the second half of the lecture? And we didn't see a significant difference there, which is important because our groups were counterbalanced by having one group see the novel videos first and the other one seeing the familiar videos first. So again, what we hope is that we see a range of arousal responses due to these videos, and that's not really a strong part of a strong component of what's causing our main result. And our data right now does suggest that there may be enhanced learning from the novel videos due to some other property other than the effect of arousal itself. And a number of our arousal indices are showing this kind of result. So limitations. So we have like low statistical power and the within subject design, a high variability, so the lecture changes overall over the course of the lecture. The content is very different. And then there's very few controlled factors between the novel and familiar videos as of right now. So moving forward, some ideas that we have, well, what we have planned for the next phase is to have a higher number of subjects. So we're going to use 30 in the next version. We had 10 previously, and a higher number of questions. So previously we had 8 total questions, 1 for each section. Now we're going to try to aim more towards 80 plus questions. And then there's a whole laundry list of ideas we have for what we can do after that. So EEG and eye tracking for measuring engagement, respiration sensing as another indice of arousal, using some sort of more controlled stimulus, like, or I should say a behavioral stimulus of like familiarity or novel exploration, maybe in a virtual environment. That says long-term memory assessment. So having a long-term memory assessment is important because a lot of the previous experiments done on novelty show an effect on consolidation of long-term memory. And doing a between subject design, which will control for cross-contamination between the two halves of the experiment and a no insertion control. And we've also been playing around with the idea of doing some sort of remote experiment. If we can surpass the technological challenges and maybe have some sort of portable sensor box, we'd be able to collect a lot more data. Thank you for everyone who's contributed to this study. And if you'd like to participate, please email Annie, who is doing all of the recruitment. And also thank you, Annie, for all your help, too. You've been contributing and helping me a lot through this. So, yeah.
Thank you. And I should do, oh yeah, it's a bit loud. Am I okay? Yeah, I have my microphone. I think he's adjusted. All right. I feel like I should do libations to the computer so it doesn't betray me. Yeah, so we have a team. I'll have pictures in a moment and I'll talk more about them. But what we were doing is taking an online physics class and putting some more computational stuff into it. So this is a very fancy title for doing that and trying to figure out what works. And so I'll get right to the point. This is an edX course, open to the world. It's been offered from the physics department a number of times. We are taking each week, taking one of the homework problems, and you should get to know this homework problem. We're going to revisit it throughout the talk. So I'll give you a moment to read it, and I'll read it for those of you who may not be able to read it. Mary wants to throw a ball straight up and then hit it with a second ball. She wants the ball to collide at a height 10 meters above the throw point, and she knows that she needs to throw the two balls 1 second apart. So if you think of somebody juggling, this would be like a trick where you throw one ball up and then you want to throw another ball up and make sure it hits right at the same 10-meter mark, and you have a second between the two. So this is a very standard physics problem. I'm sorry for those of you who have physics stress, but you don't have to solve it right now. This is not a pop quiz. But what we want to do is take this type of word problem where I'm standing up here and throwing imaginary balls, and we want to give students some type of a more engaging way to understand that content. And so we have these things are sliders that somebody can click and drag around. There's some different controls. These are the trajectories. So this is height versus time. So these are the trajectories of the balls plotted, the height of the ball plotted as a function of time. And we have Mary, who we will come back to in a bit as she goes through a very adventurous path. But I'll let myself at a previous point in time explain this a little bit more. And this is the thing, this is the ideal of what we think will be very helpful. And then we'll talk about the science about how to understand if it is helpful. So we see here a plot of the height of the two balls versus time, and Mary throwing those balls, and we have a little animation. So this slider just moves the current point in time. So you can see the ball's height is plotted along the two plots. Each of the balls has different heights, and we can control the current point in time. Notice that when these two lines are equal, the two balls have collided. So this is the point at which we're trying to solve. So I'm going to increase the speed, the initial speed of the balls, and notice that that is going to make them collide at a later time. That's because the initial ball is going to go higher, and gravity is the only acceleration. So we're going to collide at a later point in time. If we change the time between successive throws, notice how their relative trajectories are going to change. So at this point, Mary has not thrown the second ball, and as time progresses, she will have thrown it. Or I can have Mary throw the two balls very close to each other. If we watch this animation from the beginning, notice she throws the first ball, then she throws the second ball, and they collide. So you can also change the height of Mary's initial throw, and notice that does not change the horizontal position of the collision, so the initial height of the throw is not an important variable. So this is what we're hoping to engage students in, and this is not the first time we've tried to engage students with interactive widgets. But this is the first time where I'm trying to understand what about that is actually engaging, and does it in fact lead to better outcomes. So the two hypotheses that, or the two things that feed my hypothesis are that in the 1940s, there was this amazing study where they just put some shapes on a screen and then had them move around in a little video, and people anthropomorphized. They gave them human emotions and human attributes. And then I'll talk about this one in a second. So I'll let you watch this and see if just by movement you can give some sort of story to what's happening here. So by this point, people usually don't like the big triangle. And this is an amazingly universal response. You can test it with children and adults and different cultures. And it's very clear that this triangle is intimidating and bullying the smaller triangle. And that's not actually what's happening. These are literally just shapes moving on a screen, but we've given this entire emotional story to it. So just by movement, we can engage the emotional system. We can engage the human narrative system in understanding what's happening. So yeah, you get a little celebration once they get out. So the next thing, and this is really great timing. So this is a Prakash child. So my colleague Pawan has just talked about a child who has vision restored. They were congenitally blind, and then their vision was restored later. And we want to understand how the brain starts to interpret information now that it has visual stuff coming through. And so this is a child who's been asked to identify the shape on the screen. So yes, what shape do you see? And the kid says, I can't make it out. And then you start to move the triangle. And now the triangle has become this emergent object. So instead of just giving people these static images, instead of giving people just static images, we want them to engage in movement so that we can get that kind of visual learning process, that mapping of physical phenomenon onto the visual cortex. So in this course, we had 4 weeks. And so we had Mary, who started out as a juggler in a circus, and then went to become a race car driver. And so she needed to figure out if her car was going to slide on the ramp as she drove around at a certain angle. Then I think she probably came down here first and became a stunt woman and hung off of the back of a truck as it drove down a big hill. And the students were asked to find this angle. And so this involves some nice coordinate transforms and things like that. And then Mary finally gets shot out of a cannon. She goes back to the circus, and her air resistance allows her to control her trajectory so that she ends up landing on the pad. So we're engaging some type of storytelling inside of these little interactive widgets, and then also wanting students to start thinking computationally about these problems. So this is my time when I think, and I admit that I'm kind of a figurehead. And the work was actually done by these other people. Michelle Tomasic runs the online class. Anna Musser was the research methodologist who came up with this entire experimental design I'm about to share with you. Andrea Griffin built all of the tech that I'm going to talk about. And Lauren Burke is a PhD student who did all of the analysis. There's not much left to be done other than giving a talk, so I'm giving a talk. So if we return to our question, we have Mary throwing these balls. And there's this tension, especially at MIT right now, about how do I engage students in doing this type of work. I can have them do math by hand. We think that there's definitely some value in that. I can have them solve it using a computer algebra system, or just coding it, computer programming. Or I can have them interact with a widget and have them play with this thing and learn visually. And these are 3 equivalently engaging ways to learn for different people. And we want to know which one and how to give different learners so that they engage. And so this is the core of the research, is we have these 3 tense ways of learning. We only have so much time to teach. Which way should we use? And how can we tell the difference? So what we did is we have 4 types of information that we can give to students. We can give them a notebook full of code and some explanation so that they can learn how to code. We can give them a nice interactive widget so that they can play and visually learn. We can give them an interactive widget that's not visual. So this is just a table of numbers. So they can still interact with it, and there's still something living there, but it's not that visual cortex stimulation. And we can just ask them to reflect upon a little bit of extra, physics. Maybe it's really just need a little more guidance to think about the physics. And so we're taking the 2x2 factorial design in order to tease out whether visualization, coding, or just doing physics is actually the thing that's engaging these students. So the first group, we break students into 5 groups. The first one gets just the problem, Mary throws this ball. The next group gets some code and the interactive visual widget. Then we do the next group, which gets the visual widget plus some questions to reflect upon to normalize for time on task. Then we have the non-visual widget with the reflection questions. And finally, we take the non-visual widget with the coding. And so this is a standard 2x2 factorial design, standard in that our research methodologist told me this is how you actually do this type of work. And so we did it. Where we have these 5 groups, the control just gets the standard physics problem. Then we have a programming plus visual widget group, a programming plus non-visual widget group, a questions plus visual widget, and a questions plus non-visual widget. And normalizing the deltas across these groups, we can understand the performance of these different groups with those different interventions. And so the whole workflow, a student hits the course. This is kind of a timeline plot of the things that we need the students to do. So they come into the course, and we give them a pre-assessment that was graded, and you can worry about some of these details if you want. So it's a pre-assessment of demographic information, standard physics comprehension pre-test, visualization tested through spatial reasoning, and a personality trait assessment. Then they go through 4 weeks where they're getting these different interventions and they're staying within their group. So if you got cohorted into the visual widget with coding group, you always got visual widgets and coding throughout the whole thing. And then we do a post-assessment of physics comprehension, spatial reasoning, and computer programming skills. So this is the slightly more animated version of that. As well as an introduction to some of the tech that was required to do this. So edX, think of edX as the actual server with edX sitting on it. Think of the Wolfram Cloud as a different server that has some other tech sitting on it. We built out a framework to be able to throw stuff onto the Wolfram Cloud and to have seamless integration between these 2 tech stacks. So when a student shows up at edX, the server is going to ping the Wolfram Cloud and say, hey, give me the pretest. Then the student can do the pretest. We're going to take their results, put them into a database, so now we have an instance of a student with some information about them. Then they're going to go into the next week and get their first homework assignment. We're going to find out what cohort they were put into based on their pretest, and then we're going to give them differentiated instruction by sending the appropriate content down to them. They can do their homework not knowing what everyone else's homework is. And then they're going to go through that 4 weeks in a row and then get to the final post-test, which is the same thing. It's going to send a request to the cloud, get back a post-test. They'll take it. We'll be able to assess their physics comprehension, and we get that information back into our database. So at the end of this, we have information about their pretest, information about the performance on these 4 weeks of a specific intervention, and information about their post-test. So we want to look at the delta of those things. But one of the other innovations that we did, so cohorting, meaning taking people and randomly assigning them to groups, exists in MITx, but we wanted to make sure that our groups had equal variance across different skill sets. So if we had a bunch of really strong physics students, we want an equal distribution of physics among the visual widget group and among the coding group and among each of our controls. So our pretest goes through and used some standardized assessments because we don't want to have to prove that we know how to test physics, because there is a well-verified force concept inventory. And we use those to balance our groups, making sure that the variance of students who already knew Wolfram language programming were equally distributed. Physics who already had physics backgrounds were equally distributed. Students who had who thought that they were going to finish the course were equally distributed, because we don't want a bunch of attrition to affect one group and not the others. So this was one interesting innovation that came out of this project. And so this is a bit unrelated to the learning, but it was the only, we had sufficient data only to make one conclusion. The conclusion is people don't know if they're going to finish a course. It was quite surprising because we tried to balance this. So we made sure that we had equal groups with people who said they were likely to finish the course and people who said they were definitely not going to. And somehow in the end, we had equal attrition across all of these groups. So you can't just ask somebody if they're going to finish a course, which was kind of surprising to me. And then we ran a full ANOVA across all of these standardized tests. So did people who were inside of the visual widget group do better on physics, or did they gain spatial reasoning skills? And the truth is our numbers just are not big enough. We had really unexpectedly high attrition rates, and we ended up, if you look at the counts, these were not the numbers. We thought we would have 10 times those numbers, or maybe even 4 times those numbers would have been sufficient. So the truth is we can't draw any conclusions, but we've built out an entire pipeline to do this analysis. We thought if we, instead of looking at just the standardized test, just look at the overall grade, we could actually group people into bigger numbers, and that also, even though it seems like there might be something here, it's not actually. The numbers are too small to be able to trust that that variance is outside of normal. So again, we just didn't get the numbers that we were expecting. So our next steps are to run this again with more students so that we can get much better statistics. We have the whole pipeline built out. If we can figure out, if we can tease out this information about whether interactive visualization or whether coding can actually help engage learners in new ways and improve different types of intelligences, then I think there's going to be an incredible amount of interest about it. Unfortunately, we didn't get that conclusion on this pilot run. But our biggest step right now is we want to share what we've been doing. So oh, now I bumped something bad. Ooh, I'm going to let it. Yeah, but it also killed power. Oh, it is back. Excellent. Bravo, sir. Okay, I will stay away from that portion of the floor. All right. Yeah, so we've done a 2x2 factorial design, which you can do with completely random cohorts, but we did it with the balancing of the cohorting so that the variance of people with different skill sets was balanced. We also did that with real time. Because this was an asynchronous course, we needed to use a medical or clinical trial model where somebody comes in on a rolling basis and we need to add them to a group without knowing all of our enrollees yet. So we have an algorithm that's doing that real-time cohorting and making sure that even though we don't know everybody who's going to show up in our course, we're able to continue to keep balancing out our cohorts as they're built in real time. And we can now serve a bunch of differentiated instructional material to students based on a pretest. So you can ask students in the front of the class, hey, do you want videos or do you want audio recordings or do you want written text? And you can serve that content using the framework that we built out. I'm hoping that the keyboard will continue to work, but it does not. So I may be unable to progress the slides.
What does this do? Wow, it's really...
No, it's just when I bumped the thing, it like only projected the PowerPoint onto that screen, not here.
That's a new one for you.
I know, I've never seen it either. I know, I didn't make the libations. Never joke about libations. It's okay, I can go. Oh, it just worked.
Is it oh.
That was totally cool.
Sweet.
Yep, you did it again. All right. Thank you. Right. So our biggest mission right now is to get people to understand the tools that we've built and how they can use them in their course. So if you think about this whole diagram that I showed, having something sitting in the cloud that can do a pre and post assessment and build out a profile of your learner and being able to use that profile to serve differentiated content, you can use that for just pure instruction, or you can use it for experimentation, and we can help support you in using that if you want to. You can also just embed all sorts of different content. One of the things that we have done with another course is taken a really large form, which is helping students to reflect upon how they're going to engage in the course, and having that generate a PDF that they can print out and put on their desk as a little motivational thing, which is like, hey, you said you were going to work on this every morning, and here's a picture that you thought was really motivating. So we're trying to engage students through this kind of work plan creation. And we have created a step-by-step edge course. So if you want to use any of these tools inside of your own system, you can come and walk through guided deployment notebooks, which will help you set up all of the infrastructure in your own course, and we're also available to help. There is a 3-week summer program if you want to really go nuts and build out a bunch of content. We're using the Wolfram Cloud, and they offer a 3-week educational innovation program. And we'll be talking at the significant interest group coming up, so we'll get more into the tech at that event. But yes, thank you.